So today I want us to engage the question, how big is a matrix? And so what we're going to try and do is look at different ways for us to measure the size of a matrix, right? So what's one of these? What's one notion of the bigness of a matrix?
Dimension.
Okay, you can look at the dimension of the matrix. That's fine. So if it's like an m by n matrix, you would have two numbers. I guess this is kind of like your pant size. You have like two numbers. You have like the width and the length, right? So you're trying to reduce a matrix, you say that's the dimension of it. But what I want to say more is less something about like the dimension and something more about, the matrix itself, something that's trying to capture some information about, is this a particularly big matrix? Is it a small matrix? Does it have a big effect when you multiply by it, or a not so big effect when you multiply by it? So what might capture something like that? Okay, you can look at measures like rank, or trace, or what's another one? Determinant. So one of these measures we can look at is we can just look at the determinant of A. And I want to say this is going to act like we're trying to get some notions of norm today. So what is a norm? A norm is a real valued function that assigns to, in this case, a matrix, just some scalar value. But in order to be a norm, I want a few more properties to be satisfied. I want it to be non-negative. So the determinant's not going to quite do that. But if I take the absolute value of the determinant, now it's working. So the absolute value of the determinant, that's going to tell me something about how big the matrix is. And what does it tell us in particular? Well, recall that this just measures how much multiplication by A changes the area or the volume of like some parallelepiped, right? So how much this changes your area / volume when you multiply by A. In particular, the picture you might have in mind is if you begin with some unit vectors 1, 0, and 0, 1, this traces out an area 1 square. Then you apply the matrix A to it. And now you get out, well, I don't know what it is, but maybe you get some new values that your E1 and your E2 get sent to, whatever your first column of A is, whatever the second column of A is. And the area of this new guy is just going to be the determinant of A, right? Okay, the sign is just indicating if you flipped orientation or not, but absolute value is just measuring the area of this square right here if the original square had area 1. So the determinant's capturing some good information about matrices. One of the problems, though, is determinant is only defined if your matrix is square. And you can be over C or over the reals. Let me just put over whatever field you're working on. You can think of it however, over the complex numbers, over the real numbers, whatever field you want to work with. But it's only defined for square matrices. So it's like, well, I want maybe some notion of norm that's going to apply to rectangular matrices as well, non-square matrices, right? So what is another notion of norm? What is some other notion that if I have a matrix, I want to get some sense of the size of it? Well, one thing you could do is you could say, let's just treat this matrix as if it's a vector. So instead of thinking of your matrix A, so here I want to be given some matrix A, that in general I want to try and think of it as an m by n matrix over my field. But I could say, well, let's just treat it like we treat a vector. So then the norm of A, this is called the Frobenius norm, so that F is for Frobenius, this is the Frobenius norm, is just going to do what you would do if you want to find the magnitude of a vector. You would take the square root of the squares of all the values of A. So if A is given by some A11 through on top A1n coming down AM1 through AMN, this is just going to sum those all up. It's just A11 squared plus A12 squared, and you keep going until you get to the very bottom, AMN squared. Although careful, if these are real numbers, this is fine. If these are complex numbers, you're going to get out some complex entry. I want to make sure I get out some non-negative real number, and so what I'm going to do is I'll take the magnitude of all of these, so that if they're complex, they all become real numbers. Okay, so this is just treating A as if instead of being some m by n matrix, you're just thinking of it as like a vector in m by n space, right? So it's like r to the m times n or c to the m times n, and then you're just taking some analogy of the Euclidean norm, right? So that's a fine way to do it. But the problem is, it's like if you take this notion of norm, you can rearrange the elements of your matrix and the norm stays the same, right? Like you can move the element in the top left and switch it with the guy under it, or just permeate the elements around, and you're going to have the exact same value come out because these are just going to be switched around, right? And you're like, well, maybe there's nothing wrong with that, except we know that when you change just a couple elements of a matrix, you can really change the matrix, right? So like, this really isn't saying something about the linear transformation. This is just like treating the matrix as if it's just a vector and just looking at the values in it, not really respecting like what the linear transformation itself is doing. And so you might think, okay, maybe this isn't fully satisfactory. Now this is used a lot. I mean, you're probably like, you've maybe already seen in some of your other classes, like contexts where you have some data that's stored in a matrix and you want to turn that matrix into a scalar, right? And this is a very common way to do it. But it doesn't, in some sense, like respect the matrix, right? It's not respecting the linear transformation. And so I want to introduce one more norm that we're going to talk about quite a bit today. And that's called the operator norm. The operator norm. And here, I'm just going to write this, just the norm of A. It might seem kind of unnatural, but I'm going to suggest it's in many ways actually more natural. I think we'll come to see that in that it respects the actual linear transformation. So how can I define this? Well, let me just remind you. We already know what the norm of some vector is, right? If you have some vector, you can define its norm just like this, just as a Euclidean norm. So given some vector, you can define its norm by just taking the elements of the vector v1 and squaring them up through, Vn. So we know how to find the magnitude of a vector. So it's like, okay, how are we going to find the magnitude of A without just treating A as a vector? The way I'm going to do it is I'm going to say, well, let's figure out what the magnitude of A times some vector is divided by the magnitude of that vector. So A times a vector is a vector. V is a vector. So both of these norms are well defined, just defined like this, right? Although, like, pay attention, V, if A is an m by n matrix, and you then have something like AV, then if A is a m by n matrix, V would have to be an n by 1. And so when you multiply them together, you have an m by 1. So this guy on bottom, the V, is an n-dimensional vector, whereas on top you have an m-dimensional vector. But that's fine. You can take them both and turn them into scalars by doing this Euclidean norm. So we want to define it like this. But then the problem arises, like, for which vector, right? Like, like which vector should you choose so that you can then measure this difference? And the answer is we can't decide, so just do it for all of them. Just do it for all of the vectors that are non-zero, and then take the maximum of those. So this is going to look across, and it's just asking how much does A stretch your vectors by, and find the maximum amount of stretching that happens. So that's our new norm. The norm for A is the maximum amount A stretches some vector by. Okay. Another way to think about this is if this definition is a little bit confusing, you can be like, well, if we whatever vector you pick, whatever v you pick, you can scale that vector to be just 1. And scaling is an operation that respects norms. You can pull that scaling factor out. And so this ends up being the same as just the maximum of just the norm of A times V, where we insist that V is a vector of unit length. So same thing. This first one's just saying, see how much it stretches all of the V's by and take the maximum amount. Well, you can just scale that V so it's unit, and then that's just going to be whatever A times V is. Okay, so either one of those definitions will work fine for us. So it's like, what's the correct norm? Well, I'm going to do some arguments in favor of this last one, but really each of these are capturing different pieces of information about your matrix. And we could name several more that would give you other kinds of information about your matrix as well. But each of them really is saying something. And I was beating up on this Frobenius norm, a second ago, and it's like, yeah, it is kind of dumb, and that's just treating your matrix as a vector, but it does have some nice properties. So one nice property is the Frobenius norm is just the trace of, let's think. It's actually the square root of the trace of A conjugate transpose times A. So it's like, maybe there's something there that's a little bit interesting, right? It's not entirely dumb. It's related to your trace. So if that's not clear, maybe I should just convince you of that really fast. So what is the trace? Because this is saying it's the sum of the magnitude of all of the elements of A, whereas your trace is only a diagonal elements. So why are these the same? So maybe I'll just show you in a 2x2 example, but it'll be sufficiently compelling that you'll be convinced it's true in general. So A conjugate transpose A. So let's say A is some matrix A11, A12, A21, A22. We're going to take its conjugate transpose. We're going to first take the transpose, so it becomes A11, then below it is A12, and to the right is A21. So these guys switch, A22, and then take the conjugate of everything. Okay, so that's A conjugate transpose times A. And what do we get when we multiply these out? Well, think carefully. Row times column is actually, it's like this guy dotted with himself. It's the first column dotted with himself, but he's actually being dotted by his conjugate transpose, right? Because we took the transpose, row times column is actually him dot himself, but dotting with the transpose, and so that gives you A11, A conjugate transpose, plus A21, A21 conjugate transpose, which is just A11 magnitude squared, plus A21 magnitude squared. That's what we have in the top left. And then I don't care what's in the top right and in the bottom left, just care about the diagonal. But then if I want to look at the bottom right, well, it's just going to be the bottom times the right, which again is just like this column dotted himself, but actually dotted with this conjugate transpose. So it's A12 times A12 conjugate transpose, so A12 magnitude squared, plus A22 times A22 conjugate transpose, so it's A22 magnitude squared. And then you see the trace of this is just going to actually be summing up all of these elements magnitude squared, because you're just summing up the elements of one column, each of them magnitude squared, plus the elements of the next column, right? And that extends to an m by n matrix. Okay. If your matrix isn't square, well, think about it for a second, but because you're taking the transpose, it works as well, right? So in general, that holds. Trace is well defined because even if A is an m by n, you're multiplying it by the transpose, the conjugate transpose, so it's an n by m by m by n, right? This is a m by n, but A conjugate transpose is an n by m, so when you multiply them together, you get a square matrix. This is how we turn a non-square matrix into a square matrix, by multiplying it with its conjugate transpose. Okay, so hopefully that's convincing. But still, you should think Frobenius norm is really measuring something about the elements of your matrix, where operator norm is really trying to tell you something about the linear operation itself, right? So that's kind of, these are trying to get at different aspects of the matrix. Whereas determinant, it's great because it tells you something very geometric. The problem, though, is it's only defined for square matrices. So I think our goal today is to study some properties of these two norms to try and understand in what ways are they analogous to the determinant, in what ways are they not analogous. And then we're going to try and wrap up by the end, trying to see some more geometric interpretations of these, right? Like, what is this really telling us going on geometrically? And how does it relate to what we talked about last time, which was the singular values of a matrix? So that's our goal for today. And so let me just begin with perhaps like the most important, or not if it's most important, but it's pretty much like one of the most fundamental properties of determinant, something you use all the time in your introduction to linear algebra course. What can you tell me about, like, what's a really important property of the determinant? Well, in particular, what's the determinant of A times B? It's just determinant of A times determinant of B. This is assuming A and B are both square matrices, so this is well defined. But if you have two square matrices, it's just determinant of A times determinant of B. Where if we take absolute value, this is still certainly true. That's only true, as I noted, for A and B both being square matrices, so that this is a well-defined on the right. So now we might want to know, are similar things true for the Frobenius norm and for the operator norm, right? Like for the Frobenius norm, is there any relationship between the Frobenius norm of A times B and on the right, the Frobenius norm of A times the Frobenius norm of B? And is there any relationship, so that's like a question mark, and is there any relationship between the operator norm of A times B and the operator norm of A times the operator norm of B? So that's what we want to investigate. Okay, what I'm going to do is I'm going to do it for this last one, and then one of your exercises in the homework will be to do it for the second one, right? But let me do it for the operator norm. So first of all, let's just try and get a grasp on what's going on here. So when you see this, you might be a little bit confused. Just remember what we just said. The norm of a matrix is the maximum value of that matrix times V, where V is some unit vector, or more generally, it's just the maximum value of the norm of AV divided by the norm of V. So what that means, so just note, whatever the norm of, say, A is, it has to be at least as big as AV divided by V for any V in, well, somewhere I should say my dimensions of these guys. So let's say A is if A is a M by N matrix, and let's say B is a N by O, give me another letter. I can't say O because that'd be disgusting. N by L, is that bad? It's the wrong order. Will you live with that? Is that okay? Okay. So that means my V is going to be living inside of n-dimensional space, inside of Fn. It's just a vector. You don't need to worry about the dimension. But for any V you pick in your vector space. Right? Because he's defined to be the maximum of all of these. OK, cool. So now let's just take a second and think a little bit about what we can say about the magnitude of AB times some vector. Well, matrix multiplication is associative in that the magnitude of AB times a vector is the same thing as A times BV. And here BV is just some vector. So where does my V live now? See, my V no longer lives in Fn. Down here, my V is living inside of L-dimensional space. Here, my V, to be well-defined, has to live inside of L-dimensional space. And therefore, my BV is something living inside of, well, B is an n by L, so that's in n-dimensional space. But they're just vectors. So BV is just a vector. And so it's like, I have A times some vector. And I just said here, A times a vector. Another way to write this inequality is that A times your vector, that the norm of A times your vector, is less than or equal to the operator norm of A times the norm of V. Right, that's another way of writing this inequality. But here, instead of having just a vector V, our vector is B times V. So this guy should be less than or equal to the norm of A times the norm of B times V. This is vector norm. This is operator norm. We happy with that move? Yeah? Well, like if you're happy with it, let's do it again. So B times V, by this exact same argument, this is just going to be less than or equal to the norm of B times the norm of V. So what do we have here? Well, I have that the norm of A times the norm of B is greater than or equal to, let's divide by that V, ABV divided by the norm of V. The norm of A times the norm of B is greater than or equal to the norm of ABV divided by the norm of V. Kind of sounds like I'm saying normity. And that's true for any vector V, any V inside of FL. So if it's greater than or equal to this for all V, if this is true for whatever V I might pick inside of F of L, then in particular, it'll be greater than the maximum, greater than or equal to the maximum. But the maximum is precisely how we defined the norm of AB. Right? That's a definition for the norm of AB. Thinking now of just AB as a single matrix. Just that matrix AB times V divided by the norm of V. So we didn't get equality. We didn't get that the norm of A times the norm of B equals the norm of AB. But we did get an inequality. So here with determinant, we call the determinant multiplicative. Here it's not quite multiplicative, it's almost multiplicative. We call it sub-multiplicative. So it might be worth you sitting down and trying to think about, like, can you think of an instance when you actually get inequality to be a less than, right, instead of equal to. Now that might be a little bit challenging right now because this is a pretty hard definition for us to work with. And so while in some ways this definition makes sense, it's like, what can we do with this definition? So one of my goals by the end of today's lecture is to give us a much nicer way to calculate this, right? Like just looking at this definition, like this would be a nightmare for you to try and calculate. It's an optimization problem, right? It's like you'd have to do some calculus or something to solve this. And that's a little bit gross. So you might want to, like, once we have a new definition, maybe we'll come back and try and think of some examples where this is actually less than. But it's true, it's not necessarily equal to. You don't always obtain equality. And it turns out the same is true for the Frobenius norm. So I'll assign this to your homework, you can think about it. But both of these are sub-multiplicative in this way. So don't quite have the nice property of determinant, but you have something there. Okay. There's another nice property of determinants, and that's that if you take, well, we're doing absolute value, if you take the absolute value of the determinant of a unitary matrix, it comes out to just be what is it? Do you remember? So a unitary matrix is a matrix that satisfies that him times his conjugate transpose is just equal to identity. So the determinant of him times his conjugate transpose is just the determinant of the identity, which is just 1. But the determinant of u conjugate transpose times u is the determinant of u conjugate transpose times the determinant of u. And then you know that the conjugate transpose of a matrix, transpose doesn't change determinant. The complex conjugate of a matrix just changes the determinant into its conjugate. And so this is just going to be the magnitude of the determinant of u squared. But, so the determinant of u will just be 1 because we define this to be positive, right? This is the non-negative guy. So this needs to be 1. So it follows, for unitary matrix, this is just 1. So you might wonder, well, how do these other guys measure unitary matrices? So let's think about Frobenius norms, and let's think about this operator norm. Maybe I can fit it in here. Let me just erase this. So let's try and determine the Frobenius norm of a unitary matrix. Anyone have a nice argument here? Well, this first definition of the Frobenius norm may not be too helpful, because you have all of these elements, and it's a unitary matrix, they could be whatever. But if we use the second definition, that is just the square root of the trace of u conjugate transpose u, you're like, we just said that's identity. And the trace of identity is just yeah. So actually, I guess this is a little bit concerning. I was thinking that this would come out to be 1, but it's not 1, is it? You're going to get something like n. So I guess that won't quite do the work that we want. Okay. I guess that's not a problem. Let me just think really fast. Like this is going to impact us in about 5 minutes. No, it's not. This is fine. So this just comes out to be the square root of n. Oh, well, okay. We need to say where your unitary matrix U is. If U lives as a square matrix that's n-dimensional, an n by n matrix, then that's just the square root of n. Okay, so it's not 1. Sorry. I kind of hoped it would be, right? Like, it's not. That's okay. How about the operator norm? What is that going to be for a unitary matrix? How do unitary matrices change the magnitude of vectors? If I take some vector v, like how does the magnitude of this compare to the magnitude of just v? How are those related? We actually covered this a few weeks ago. Do you remember? Why?
Because unitary matrices only rotate or reflect.
Yeah, so you think of it geometrically, it's a rotation or reflection. I'll use that argument in a moment. You can also just think of it algebraically, since it's like the magnitude of uv squared is just uv dotted with uv. We've actually done this proof before, which is just dotting is multiplied by conjugate transpose. So it's v conjugate transpose u conjugate transpose u v, and then your u conjugate transpose is just identity. So that's just v conjugate transpose v, which is the magnitude of v squared. And then your magnitudes are non-negative, so you can take square roots and you recover the fact, right? So this leaves it the same, and therefore by our definition, since it's the maximum, since this should be the maximum of this divided by this, well, it's always going to be 1. So this one is just 1. Okay. So the operator norm is just 1. The Frobenius norm comes out to be the square root of n, and your determinant is just 1. So there's something there. Well, let's get to what I've been trying to build up to. Let me remind you of the singular value decomposition theorem, which says that for any matrix A, we can write A as U sigma V conjugate transpose, where, and okay, I won't write the whole theorem here. Recall U is just the eigenvalues of, I think it was A conjugate transpose, the eigenvectors of A conjugate transpose. V are the eigenvectors of A conjugate transpose A. U and V are both unitary matrices. U and V are unitary matrices. And sigma is, it's trying to play the role of being your it is a diagonal matrix. It is a diagonal matrix. And it's trying to play the role of just being your eigenvalues of A, but A is not necessarily square, right? So sigma is something of the form sigma 1 through sigma k, whatever these are. It may not be a square matrix. You have zeros over here. You might have like zeros coming down like this. It may not be a square matrix. Or it might be that this is if it's this is an m by n. So this is what it looks like if n is bigger than m. You might also instead have your m be bigger than your n, in which case it might look something like this, sigma 1 down through sigma k, and then more zeros down here. So some kind of diagonal matrix, but not necessarily square, right? Where those sigma values, where your sigma I are the square roots of the eigenvalues of A conjugate transpose A. A conjugate transpose A is positive semi-definite. So its eigenvalues are greater than or equal to 0. So when you take the square root, you get that all of your sigma I are non-negative. Right? This is what we talked about last time. So I remind you of that construction. here A can be any m by n matrix. Then your sigma is also an m by n matrix. And your two unitary guys either side are square matrices. Necessarily, unitary matrices are square. So sigma is the same size as A with two square matrices on either side. That was last time. So let's think for a second how this relates to our various norms. The first one I want to think about is the determinant. So it's like, what is going to be the determinant of A? How does it relate to this? Well, we can just use a decomposition. The overall thing is, okay, to even talk about determinant, we have to be limiting our attention to a square matrix. So we can only even have this conversation about determinant if A is a square matrix, which is the special case of this. So this is why I'm not super satisfied with determinant. This is why we talked about the other norms. But if you happen to be a square matrix, then all of these are square. They're all n by n matrices if A is an n by n matrix. And then so you can write this as just the determinant of U times sigma times V. So that's just the determinant of U times the determinant of sigma times the determinant of V conjugate transpose. But your U and V are unitary. So we just reminded ourselves that the determinant of a unitary matrix is 1. So these guys drop out. They're just 1. That's just 1, and that's just 1. So you just have the determinant of sigma. Sigma, it's now a square matrix. And so the determinant of sigma is just going to be the product of all of your sigmas. This is just going to be the product of your sigma 1 times sigma 2 up through sigma k. And in fact, in this case, that's just the product of your eigenvalues, right? So when you have a square guy, it's just your eigenvalues. Okay. But here we're represented as the product of our singular values. Okay, so knowing your singular values, you can recover the determinant of A. What if your A is not square? So let's go back to this more general case where A is some m by n matrix. And what if I want to calculate something like the Frobenius norm? So I want to calculate the Frobenius norm of A. Well, certainly I can write A again with its decomposition, its singular value decomposition, as U sigma V conjugate transpose. But it's like, I'm not going to get equality by breaking that up. We said it's not multiplicative, it's sub-multiplicative. So I could get an inequality here by saying it's the product of U and sigma and V conjugate transpose. But then it's like, I don't even know what the Frobenius norm, the Frobenius norm of your U and your V will just give you like the square root of m and the square root of n. I'll get a nasty square root of an inequality. That doesn't seem like the right way to go, right? Instead, what I want to do is I want to go all the way back to my definition. The Frobenius norm of a matrix is the trace of its conjugate transpose times the matrix and then square rooted. So by definition, this should just be the square root of the trace of the conjugate transpose. The conjugate transpose of a product changes the order and then takes the conjugate transpose of each piece. So now V is at the beginning. V conjugate transpose becomes V. Then you have sigma, which is now sigma conjugate transpose. Then you have U, which is now U conjugate transpose, times the matrix, U sigma V conjugate transpose. Okay, I wrote sigma conjugate transpose here. Remember, sigma is real and it's diagonal, and therefore, like, what is this really? Well, if it's a square matrix, it'd be unchanged. If it's a rectangular matrix, you're just changing from like this to this, right? So we'll leave it there. You could just think of a sigma transpose because the conjugate's not doing anything. This is all real values. But it's not a significant change. It's changing from this to this, or vice versa. But here we start seeing some simplification that can happen, because U conjugate transpose U is just identity, so those cancel. And so now I just have the trace, the square root of the trace of V sigma conjugate transpose sigma V conjugate transpose. And now I'm going to use a property of trace that we've discussed before once or twice. I think it's come up twice now. And that's that you can't break up a trace the way you can break up a matrix, but you can commute its elements cyclically. That is, if you have a series of products of matrices and you have one matrix at the end, you can instead move that matrix to the beginning. And you should kind of convince yourself that why does this make sense? Well, in order for trace to be well defined, this has to be a square matrix, right? This like series, this product has to be square, which means like the first value of the first matrix, V, what is V? V here is a n by n, right? Like the first dimension has to be, say it's n, then whatever the other dimensions are, the last one also has to be n. I mean, certainly we see that here because it's just V and its conjugate transpose. But in general, when you have a product of matrices, in order to take its trace, in order for it to be square, the first and last value have to be the same. And therefore, multiplication will be defined, well defined between matrices if you move that guy to the beginning, because that n and that n match up, right? So you should think that's why, that's a necessary condition for the cyclet permutation to even make sense. But in particular, that thing gives us the trace of V conjugate transpose V times sigma conjugate transpose sigma, which V conjugate transpose V is just identity. So now you just have the trace of sigma conjugate transpose sigma, but what is that? What is the square root of the trace of sigma conjugate transpose sigma? Great. It's just the Frobenius norm of sigma. Right. So just like above, how you have the determinant of A is just the determinant of sigma, here you have the Frobenius norm of A is just the Frobenius norm of sigma. That's what we were proving. And it's like, what is the Frobenius form of sigma? Well, just like look at the guy. And I mean, you can use either, whatever definition, I mean, the trace only makes sense if it's square. If it's not square, you're just taking the sum of the magnitude of all of its elements. These are already non-negative, so this just comes out to be sigma 1 squared plus sigma 2 squared all the way through to whatever your last sigma is, sigma k squared square rooted. So we're starting to see now, okay, these singular values are quite nice, because with these singular values, you can already calculate both the determinant and you can calculate A, right? The Frobenius norm of A. So the last thing you might want to ask then is like, well, is there some secret connection between the sigma values and the operator norm, right? This is our last norm. And wouldn't that be nice? Because this definition is totally inoperable, right? Like this is like not a definition you can go out and calculate things with. So wouldn't it be nice if we could just find some definition in terms of your sigma 1 through your, in terms of your sigma values? It's like what is the operator norm of A equal to? And maybe there's some nice formula in terms of your sigmas. So like now is a second I want us to think for a second. I want to suggest like the answer is like right in front of you. You already know what the answer is. And the answer to this falls out not from writing this decomposition and thinking about it algebraically like we did above, but just thinking about what this is telling us geometrically. Like, do you remember the story? Like, what is the story that this is telling us? Maybe I'll make some room here and I can like remind us of the story. See, this theorem is really giving us a geometric story of what a matrix A is. So here, I have some map from, it's an m by n matrix, so it's a map from n-dimensional space to m-dimensional space. And it's like, what does that map look like? What does A look like? And last time we told ourselves, well, to think about what A looks like, instead we can take this longer route, where A is really the same thing as first doing V conjugate transpose, and then doing sigma, and then doing U. But your U and your V are unitary matrices, which are either just rotations or reflections. So if you begin with a unit circle here, like all the vectors of length 1, right? So here are all your various vectors of length 1, like they lie somewhere on this unit circle. All V is going to do is rotate it somehow. V just plots this back down as a unit circle, having rotated it somehow, whichever way, or reflected, maybe a reflection, maybe a rotation and a reflection, some combination of rotation and reflection. But it's still a unit circle, it maps it to itself. What does sigma do? You remember? It's just diagonal, sigma 1 through sigma k. And so sigma is just a stretch matrix that will be stretching by sigma in your various directions. In one direction, you're stretching by sigma 1. In another direction, you're stretching by sigma 2. You can think of it as in higher dimensions, turning a unit sphere into a unit ellipsoid, right? It's just stretching by whatever your sigma 1, sigma 2, and so forth are. And then, what does your U do? It's just rotating / reflecting that ellipsoid, this ellipse. And so I think last time we ended up with something like this. But still, it's just some ellipse that's been stretched by sigma 1 in one direction and sigma 2 in some orthogonal direction. And perhaps, higher dimensions, you'll have more sigmas. And so now let's go back to the definition. What is the norm of A? We define it to just be the maximum amount that a unit vector gets stretched by. It's like, well, your unit vector is just some vector that's somewhere on here. Just one of these vectors somewhere on here. What's the maximum amount that vector is going to get stretched by? Well, what's the maximum amount it gets stretched by here? Whatever the longest sigma is. Yeah? Here your sigma 2 looks like it's longer. And so that's going to be the most the vector stretched by. If you're over here, sigma 1 is the least it's stretched by. And if you're in between, you're something between sigma 1 and sigma 2 being stretched by. So this is just going to give you, this just turns out to be the maximum of whatever, whichever sigma is the biggest. So the maximum of your sigma I. The maximum of your sigma I. And so one of the things that the SVD theorem gives us is it gives us this sigma, the singular values. Once you have your singular values, you can just immediately determine the determinant, the Frobenius norm, and the operator norm, right? It's just like, you just look like, which one's the biggest? Like last time we had some matrix, I think its singular values were 1 and 4. And so you're just like, so its norm is 4. The most it's going to be stretched by is 4. Whereas if you look at this definition, man, this would be a really hard problem, right? You have some 3 by 3 matrix, you're multiplying it by some values x, y, z, and then you have some system of equations, you have some polynomial where you have, variables x, y, z, and you have some constraint, x squared plus y squared plus z squared is 1, and you want to optimize that, and it's good luck, right? Calculus, I guess you can do it, but it's quite a mess. Whereas here, you can just read it off once you know your singular values. Okay, we'll stop there today.